building. And thank you, Applied Physics team, for inviting me, and KBI for hosting. It's really, really good to see some good old friends. I will be talking, those of you who have heard my talks before, it's about spectroscopy, and as Amber said, mAbs and ADCs, and I'll touch just a little bit on AAVs. So thank you, Jesse, for the wonderful introduction to AAVs field as a new modality. So it's absolutely great to hear. For those of you who are not necessarily looking at structures, although you're in the Biophysics Summit, you probably know all of this. There is an FDA guidance for industry in 2015. So you at KBI, lots of techniques. Everybody knows and loves these techniques. What I want to point out from this whole wonderful table is that only spectroscopy and X-ray crystallography and NMR can access structure directly. What I mean by directly is you can literally read it from the spectrum, right? So you don't have to do anything. You don't have to do any equations. You don't have to do really anything. And out of those, X-ray is obviously difficult. It's for solid state. And the NMR has come up over the last 20, 30 years. It's a wonderful technique, but it's expensive. It's not something that biosimilar companies, for example, can easily access to. It's not even, it's not that easy, and it's easy, but it's not as fast. So that leaves us with molecular spectroscopy techniques. And that means far UV, CD, FTIR, and Raman. There are 4 or 5 techniques, but those are the 3 major techniques. And only FTIR and Raman can be used as is for the sample. So you don't have to dilute, you don't have to detergents out and things like that. CD is wonderful, and I will show you lots of wonderful results. But those are the advantages and disadvantages between the 3. The advantage of CD is because you can use dilute samples, whereas much more difficult for IR and Raman. So each one of this, and so I always recommend to use everything in test. We too use applied photophysics, even though BioTools is known for commercialization of vibrational circular dichroism and Raman active optical activity, and bringing infrared to the field of monoclonal antibodies 20, 30 years ago, whenever that was. We could, of course, make a CD spectrometer ourselves, but there was no need to because applied photophysics has a marvelous CD spectrometer. And I'm a big fan, even though people think I've spent 20 years talking about not using CD. That is not true. I've always loved CD. It's in my thesis. So we have a wonderful collaboration, and I'll tell you a little bit about this with applied photophysics. I've just described the differences and advantages, disadvantages. They all calculate secondary structure, and you can get qualitative and quantitative information from each one. So why am I talking 30 years later again and again about the good old CD and FTIR? The answer is because, and hopefully I'll convince you, because the correct structure matters. It really does matter. It matters for all the different industries. What I found by attending a higher order structure meeting and finally tuning into what people were saying when they were giving talks is I was kind of shocked that the structure was not correct from lots of different papers and presentations and all of that. So I went back and I said, I need to fix this. I need to tell the audience how to do this right. And so that's why we are here yet again. My take here is, can the industry, meaning biopharmaceutical industry, can the industry agree on methodology? And I'll show you where the problem is in just a second. And then, of course, I'm super excited to introduce this breakthrough algorithm for CD analysis. It was my dream when I was a graduate student. People told me it wouldn't work, but it works like magic. So I'm very excited to show you that. I'm going to show you the examples on mAbs, ADCs, and GLPs, and I'm going to introduce what we are calling spectroscopic potency index for AAVs. AUC will forever be a gold standard. No question about that. There has to be an easy, actually, John asked $1 million question. Do we have something that's easy and fast? And hopefully we do, and we're looking for more and more collaborators. We'd like to have a very, very definitive answer to this. So let me start with NIST monoclonal antibody that most of you who work on mAbs know and love. At the HAS 2017 meeting, there was after the HAS 2017 meeting, there was a write-up. I know lots of people that I've known over the years are co-authors, and it's a full biophysical characterization on mAb. which lots and lots of people go to. They can see how the techniques are to be done. And in addition to these chapters that I'm showing, a document case study, how to submit, you can find all of this online. NIST sells this antibody, which can be used as a standard. It came from, I believe, MedImmune, and they decided not to proceed, and it became a standard for the industry. So it's a mAb. It's IgG1, and you see the RM number. But if you look at all of these publications very carefully, as I finally did, all papers, every single document discusses secondary structure and determination of secondary structure using CD and FTIR, but none show any quantitative structure. I have gone through every single document I can find on this, and not a single one shows definitive secondary structure. This is what you see. So you see something like this for FTIR. It's an intermolecular beta sheet, has a second derivative at 658, blah, 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 blah. So it's assigned it to beta sheet, right? And then for FAR UVCD, it says 22-2018, assign it to beta sheet. And that's it. But there are so many pharmaceutical companies, we too, in a 100 smaller scale than KBI, do characterization. We specialize in secondary structure characterization using advanced techniques. And maybe we have smaller companies, but over the last 20 years, everybody wanted secondary structure numbers. Everyone. And so we've had the algorithms. KBI actually has our FTIR spectrometer applied for the physics CD. And so in FTIR, we've always had secondary structure numbers. Now, what's the chaos? What did I just discover starting last? So for over 50 years, people have used mathematical chemometrics approach that was started in 1969 with Passman and Moody and lots of people, Bonnie Wallach and Alison Rogers. There's thousands of spectra on the databases out there. The drawback of that is different types of chemometric algorithms and different databases will give you different results. You can go to all of those databases, you can put the same protein, and you're going to get a different result. So people have done CD with quantitative analysis. It's just not issued to NIST. With FTIR, there are two approaches. We've put 25 years, 30 years, we've used a very similar approach to CD. It's based on chemometrics with our own database. But the second approach that a lot of people use is band fitting. The drawback is the same for the first one is the same as CD, different algorithms, different databases will give you different results. But the band fitting approach has several problems: reproducibility, frequency assignment, and incorrect structural description from X-ray. And that's where the problem lies, I have discovered. I'll show you this. Let me talk about incorrect structural description from X-ray. So back in the day, I think it was in the 1980s, when the protein database was being established, there needed to be a way to take an X-ray, a PDB file, and determine what is the secondary structure that comes through. And there were two very famous groups that published papers on how to do that. One was Levitt and Greer. Back in the 80s, the whole spectroscopy field, including CD and FTIR and VCD at the time, have decided that the correct descriptor for spectroscopy is Kapsch and Sander. There was lots of papers on it, and you can see this many different ways. One way you can see that is if you go to Protein Databank, which is no longer hosted by Brookhaven, and I think I have it over here in just a second, you will actually see a program called DSSP that allows you to calculate secondary structure from X-ray. So they too adapted Kapsch and Sander algorithm. Levitt and Greer was there, but it's not adapted by anyone, except for this wonderful paper from Nature. But it's a paper by Professor Aichan Dong and his collaborator in China, both of whom are friends and customers. And they have published this result in that paper. That paper is one of the biggest downloads on how to use FTIR for secondary structure determination. And what you will see here in very small letters is that they're using a descriptor from Levitt and Greer. So this is their X-ray structure for which they used to figure out how to band fit. So they took the X-ray incorrect descriptor and learned and practiced and figured out the best methodology to do the baseline correction and then benefit the second derivative or the convoluted spectrum. But what you see here, and they don't have con A, I guess I didn't cut con A, but it's a wrong descriptor, and I will show you why. So just to give you a couple of references, here's Caption-Sandra algorithm. The DSSP program is part of the protein data bank. It's part of the lots of different places you can find it. You can put a 4-letter code like 6LYZ, 1CNA, whatever you want to put in, and you will get exact secondary structure. It's also, if you use BestCell, some other CD and processing CD data, it's also here where you can calculate secondary structure. So BestCell also adapted. I mean, everybody, I don't know anybody who uses Levitt and Greer. So every algorithm out there uses captions. So let's talk about what Levitt and Greer does for high alpha helical. And unfortunately, I don't have the conjugates A here. I guess there is in the mutant globule. We could use that. So you can see that IgG using Levitt and Greer shows 65% beta sheet. 65%, right? Now think about that for a second. Let me show you a spectrum of conjugates A. Conjugates A is a perfect anti-parallel beta sheet. It has two, you could see in the infrared spectrum, it has two peaks. They're known as E parallel and E perpendicular. And it has absolutely the highest beta sheet that we can find in PDB using Caption-Sanders. Like if you type, ask ChatGPT or somebody or ask PDB, find me the highest beta sheet in PDB, Con A would be one of those proteins. And Con A comes up as 40, 45, maybe at the highest % beta sheet. This antibody looks almost like Con A, but the second band at the higher frequency is not as resolved as it is on Con A. It's shifted a little bit, but it's almost identical structure. So how can we expect a NIST antibody to have 65% beta sheet? To me, that makes absolutely no sense. And it all comes back to that description and trying to fit the band, and anybody can fit a band any way they want. You ask me to fit something, I can get you 60, 70% if we want to. Okay, so that's comparing to Con A. But I wasn't, I know people will say, Rina, you're prejudiced. So I went to somebody I know well, a friend and a customer at Regeneron, Dr. Igor Dukor, and I asked him, is there a structure from NMR? Because there is no full structure in PDB. There is only fragments, right? If you go to protein data bank, there is only fragments of antibodies. There is no full structure. And all of those fragments come up as 43, 45%. So this is what he wrote to me. I downloaded the NIST chemical shift deposited, blah, 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 blah. I read that and I'm like, oh, perfect. That is exactly what we have been getting for the last 30 years on FTIR as beta sheets, as a beta sheet, 4% helix, 42% beta sheet. So that is a structure. That is a secondary structure based at least on the FTIR and NMR and crystal structure using Caption-Sanders. Okay, so that solves that problem. So if you ever wondered what the secondary structure was, that is a secondary structure from all the techniques. Now, what is the other difficulty with CD to me? Is in order to calculate the secondary structure, you have to put in, and I don't know if you can see this, but you always have to put in, maybe you can see it here, please enter, you have to put in extinction coefficient, or you have to put in exact concentration. And when we started doing CD, I just couldn't make any sense. I just couldn't find numbers. Like I have a book of extinction coefficients back from my graduate days. I went online, I tried to calculate tyrosine, nothing matched. So I was like, okay, let's go back to my idea of 40 years ago, was 30 years ago. And we came up with an algorithm that doesn't require any of that. So I'm thrilled to sort of officially introduce, I softly introduced it at the Haas meeting a couple of weeks ago, a breakthrough algorithm that requires none of it. If you have an applied photophysics CD spectrometer, we can calculate secondary structure in 30 seconds. You don't need anything. You don't need to go look for anything. You don't need to put it in any formulas. You don't have to do anything. Just give us a spectrum or take the spectrum yourself, and you'll get secondary structure. And I can now show you some results on mAb. So there is NIST, and then there is another mAb. There is your beautiful far UVCD spectrum from HeriScan, and there is our numbers again, just as we expect them. And here's FTIR, and they all match. There is no problem matching CD and FTIR. When I asked some of the speakers who presented 65% beta sheet why it is so high, the response was literally a sentence from my thesis, which is CD and vibrational spectroscopy techniques will give you different results for helix and sheet, because CD predicts helix better. It's N to N plus 4, so it captures the whole 3.6 residues of an alpha helix. The beta, the FTIR, or all vibrational techniques predict beta sheet better because it's N to N plus 3 in terms of the coupled dipole-dipole interaction. And I can go over that if somebody is really interested in it. But the bottom line is it's not that different, and I can prove it right here. So you can see IR actually underpredicts a little bit sometimes, but we can get almost identical results within what we've established as 5%, plus minus 5%. So that's mAb. Here is that's highly beta sheet protein. Here is highly alpha helical protein, peptide for GLP. Everybody, you turn on the TV, everybody is doing GLP. In Florida, it's on every block. Compounding pharmacies are everywhere. So here is your gorgeous far UVCD spectrum at 70% helix, as we expect. And here is your gorgeous FTIR at exactly the same numbers within percent error. All calculated within seconds. Okay. And Raman does exactly the same. So here is a Raman spectrum, and we also get the same number. So now you can do IR, CD, and Raman if you have a Raman. I'm just going to spend about a minute talking about Raman. I know it's not in my talk, but it's not in my title, but I'm just going to mention it because I think KPI does have Raman. So then I'll mention it a little bit. Raman combines it's a vibrational spectroscopy technique. So it combines the sensitivity of FTIR, but it can do secondary and tertiary structure compared to FTIR. So it's like CD in the sense that it can do both at the same time. In fact, you can literally read from left to right or high frequency to low frequency, and you can go like, okay, I know what the amide 1 is, it's a beta sheet. I know what's happening to my tyrosines and tryptophans and phenylalanines, and you can go right through it. You can come to an amide 3, and you can also look at the structure and confirm it is exactly what it is. And then you can come to the disulfide bond. So Raman to me is sort of a third technique. Nobody really uses it. CD is a number 1, FTIR is number 2. But I feel that especially for some new modalities like oligonucleotides, Raman is far more sensitive than anything else. So I encourage you to at least try it, because oligonucleotides have a really, really strong spectrum in the carbonyl stretching and then in the sugar regions. So it's a third technique if you cannot answer your question. And in fact, I can't really talk about this, but we have a collaborator, and I can't show you any of that spectrum either. But if you cannot measure a tertiary structure from CD because you have an ADC and because your conjugate is chiral, which will change your CD spectrum. Hopefully, our collaborator will be able to present soon. It's an awesome study, and we are just writing the paper. It's just fantastic because CD is a chiroptical technique. Okay, but I can show you, in addition to this, what I just showed you here, I can just show you a couple more. You can see on the map exactly what I just showed, but if you have ADC, you can actually look at some of the drug conjugates and see what's happening between different ADCs, different lots, comparability studies, different payloads, different maps. So let's talk about AAVs for a second. I don't have as many slides, so thank you, Jesse, for introducing and doing such an awesome job. We too purchased lots of AAVs, And we too found that it was almost impossible to find any full characterization. So we were lucky enough, ex-customer reached out, remembered my name, and asked if we could find a faster, easier, better methodology. So they had very nice, clean AAVs. So this is actually from that same company that, Jesse, I think you used. But this tells you, if you know FTIR spectroscopy, this tells you everything you need to know, right? You can see right away why, when I got COVID in 2021, I was sitting there and just wouldn't move because I saw the spectrum and I was like, oh my God, this is amazing. But I will tell you that for AAVs, CD is much better because remember the advantage of CD spectroscopy, it's lower concentration, right? AAVs have very low concentration. And I hope you can see this. I don't know if you can, but just as in the UV, we have different bands for protein and nucleic acid. But remember, CD is chiroptical technique. Remember that DNA and proteins are chiral molecules. Remember that we have a much better separation in CD between proteins and DNA. What we have been able to show, and unfortunately I can't really show you the results just yet, but we have been able to correlate CD absolutely beautifully to potency. We decided, we looked at full versus empty ratios, and we did all of that. We used a Japanese paper as well. And then we said to the customer, to this collaborator, do you guys have potency numbers? Can we just correlate the potency? Because this is so fast. And it's a beautiful sort of, I think, complement to AUC because you can measure all the spectra and then you know which ones are good, which ones are bad. You know almost right away from this correlation which ones are going to be good and bad, and then you can go back to AEC and get all the information that you presented. So I feel like it's a great, great compliment. So if you're in the audience, or even to my friends at KBI, we're looking for collaborators to prove that this algorithm is robust, because different people have obviously different single-stranded DNA. They might have different capsids, different single-stranded DNA. So we absolutely want to make sure that the algorithm works on all the different types of AAVs. So please reach out to me, and hopefully we can show all of that. With that, I want to thank everybody online and thank the audience here, and hopefully we can have a really nice discussion.